Welcome to this in-depth geospatial lesson. Today, we are going to explain one of the foundations of modern positioning technology. How GNSS accuracy works, from raw satellite signals to centimeter-level precision. If you use GNSS for surveying, mapping, drones, agriculture, construction, autonomous vehicles, or disaster response, understanding this accuracy pipeline is essential. Let's begin. What GNSS is and how positioning happens. GNSS stands for Global Navigation Satellite System. It includes systems like GPS from the United States, GLONASS from Russia, Galileo from Europe, Beidou from China, and regional systems such as QZSS in Japan and NavIC in India. Each satellite broadcasts radio signals that contain orbit information, time stamps, and encoded data. A GNSS receiver measures how long those signals take to reach it, and since radio waves travel at the speed of light, the receiver can convert time into distance. This estimated distance is called a pseudo-range, because it still contains errors. To compute a precise three-dimensional position and time correction, the receiver needs signals from at least 4 satellites. Why raw GNSS is not fully accurate? Although GNSS is incredibly advanced, raw satellite measurements face several challenges. The ionosphere, located high in the atmosphere, slows down signals because of charged particles. This alone can introduce errors of several meters. The troposphere, which contains weather systems and water vapor, also bends and delays signals slightly. Satellite clocks and orbits are not perfect, so even tiny timing or orbital uncertainties translate into distance errors. Receivers themselves introduce small electronic noise. Additionally, reflected signals from buildings, water, or metal surfaces, known as multipath, can confuse the receiver. Finally, the geometry of satellites in the sky matters. If satellites are clustered in one direction rather than spread out, accuracy decreases. This is known as poor satellite geometry or high dilution of precision. These combined factors mean raw GNSS typically provides 3 to 10 meters of accuracy under normal conditions, and sometimes worse in urban environments or forests. Technologies that improve GNSS accuracy. To move from meter-level accuracy to centimeter-level precision, we apply augmentation techniques. The first method is satellite-based augmentation systems, or SBAS, such as EGNOS in Europe, WAS in North America, GAGN in India, and MSAS in Asia. SBAS transmits atmospheric corrections and integrity information, improving accuracy to about 1 meter. Another method is differential GPS, or DGPS, which uses a local base station to correct satellite errors. DGPS typically improves accuracy to under 1 meter. Next, real-time kinematic positioning, or RTK, uses detailed carrier wave measurements and real-time corrections from a base station or network. RTK provides centimeter-level accuracy almost instantly and is widely used in surveying, agriculture, machine control, and drone mapping. Finally, precise point positioning, or PPP, uses highly accurate satellite clock and orbit data instead of a local base station. PPP provides global accuracy in the centimeter to decimeter range, but it requires some convergence time. Code versus carrier phase. GNSS receivers use 2 types of measurements. Code-based measurements determine distance by comparing the timing code in the satellite signal. These measurements are fast and reliable but are limited to meter-level accuracy. Carrier phase measurements use the underlying radio wave itself, measuring tiny phase differences. Since the radio wave wavelength is only a few centimeters long, the resulting position can also be precise to a few centimeters. However, carrier phase processing is more complex and requires solving ambiguities. This is why survey-grade receivers deliver centimeter accuracy, while smartphones generally do not. Single frequency versus multi-frequency GNSS. Some receiver models only track one frequency, often called L1. These single-frequency receivers work well for basic navigation but cannot fully correct atmospheric delays. Dual-frequency and multi-frequency receivers can compare delay effects on multiple frequencies, allowing them to eliminate much of the ionospheric error. This improves accuracy, reliability, and convergence speed, especially in challenging areas such as forests, cities, mines, and mountainous regions. In simple terms, more frequencies equals more accuracy and less signal interference. Smartphones versus survey-grade GNSS. Modern smartphones do receive GNSS signals, but they have limitations. They contain very small antennas designed for convenience, not precision. Many phones operate on only one main GNSS frequency, and while some support multiple constellations, the processing is optimized for navigation, not centimeter positioning. Survey-grade GNSS receivers, on the other hand, use geodetic quality antennas, track many constellations and frequencies, and support scientific correction methods like RTK, PPP, and DGPS. As a result, smartphones typically achieve 3 to 10 meters of accuracy, while professional GNSS equipment achieves 1 to 2 centimeters. Why multi-constellation matters. Using more satellite systems at the same time, such as GPS, GLONASS, Galileo, and Beidou, provides more satellite visibility. This improves satellite geometry, reduces outages, and increases accuracy and reliability in urban areas, forests, and other obstructed environments. This is why modern survey equipment uses multi-constellation GNSS instead of relying on a single system like GPS alone. Real-world applications. GNSS accuracy is essential in cadastral and engineering surveying, highway and railway construction, precision agriculture and automated tractors, drone flight control and photogrammetry, earth deformation and landslide monitoring, marine and aviation navigation, timing for telecom and power networks, autonomous vehicles and robotics. Modern infrastructure depends on reliable positioning. A small error in GNSS can result in major navigation mistakes or structural misalignment, especially in industries like aviation, mining, and surveying. If you found this explanation useful, please like, subscribe, and share. And comment below. Do you use RTK, PPP, DGPS, or standard GPS in your work? Thank you for watching. I'll see you in the next video.